All right. If I gave you a linear equation or quadratic equation, would you be confident in solving it? Yeah, we've worked with solving equations since Algebra 1, right? So for some of you, 7th, 8th, 9th grade, all right? A long time ago. All right, so what we're going to do now is we're going to mesh them together with some trig. Here is like the very, very basic example of solving a trig equation. Sine of x equals 1/2. Okay, so what are we looking for? We are looking for where sine of x is 1/2. Does anyone know it off the top of their head? Hmm? 5 or 6?
Yes.
5 or 6? 5 or 6, is that the only one? Okay. 5 or 6, are those the only two?
No, because you can just keep going.
Okay, if we think about graphically, okay, don't draw the graph, okay? But if we think about graphically, here are the two that you guys pointed out to me, pi over 6 and pi over 6. But then it's going to happen over and over and over again because the sine function is periodic. It repeats over and over. Okay? A lot of you are thinking about the unit circle. Okay? Pi over 6 and 5 pi over 6. That's it, right? Well, technically, we can keep rotating around the unit circle over and over and over again, and we can go over those points over and over and over again. Okay, so technically, we're going to have an infinite number of answers when we solve these trig equations. Now, you can't write infinite solutions, okay? You have to actually explain to me what those solutions are, okay? Now, up here, with our sine graph, how often does our sine graph repeat? 2 pi, okay? So we can take into account that we have a value and it's going to repeat in every period of that function, okay? So this is how we are going to solve trig equations. Okay. First of all, we're going to go back to our Algebra 1 ways, okay? If it's a linear trig equation, we're going to isolate that linear piece. Okay? Back in Algebra 1, if it was linear, you got x by itself. So here we have a trig function. If it's linear, we're going to get that trig function by itself. Sine, cosine, tangent, whatever it may be. Okay? If it is not linear, then you need to set it equal to 0 and factor. We can only factor if our equation is set equal to 0. There will be numerous times where we will have to factor. We may need to fall back on our fundamental identities to help us. Okay, if we cannot factor one of our equations, it is possible for us to use an identity kind of as a last resort to rewrite it, so then maybe we can factor it. Okay, and I'll show you what I mean today in one of our examples. And then I'm going to come back here. We had this solution of pi over 6, and you told me it was going to repeat every 2 pi, correct? So a way to express that solution is, well, this one would be pi over 6 plus 2 pi. And then the next one would be pi over 6 plus 4 pi. And then we could just keep going every 2n, or every 2 pi. So what we're going to do to describe that is we are going to write our solution. So what angle does it satisfies the equation? And then we're going to add the period times n to describe all of the different infinite number of solutions that will come in every period of the graph, or every rotation around the unit circle.
N has to be full.
Huh?
Does N have to be full?
N is representing an integer. Okay, so we can go backwards multiple periods, or we can go forward multiple periods. So if we talk about sine of x equals 1/2, then we would write our answers as x equals pi over 6 plus 2 pi n, and x equals 5 pi over 6 plus 2 pi n. We would give the two answers and then add the period times n at the end. So, basically, we just need to do a lot of examples. Okay? Yes.
So are these all gonna be like, we're gonna end up with angles that we know, or are we gonna have to use?
These are all going to be unit circle values. Okay? We're not going to use our calculator. All right? That's a good question. Not in this chapter. Okay? This is a non-calculator kind of chapter. Okay? But chapter 6, we'll pull our calculators back out. Okay? All right. So first example, we'll start soft, and then we'll get more intense. Okay, so ideas on what we should do. Okay, we have sine of x on both sides. We probably should bring those together. So this negative sine of x, we can add to both sides, right? So we have 2 sine of x plus radical 2 equals 0. Now this is what I would consider a linear trig equation, because we just have a sign and it doesn't have a power, okay? And so in this case, we need to isolate that trig function. So how do we do that? Okay, subtract over the radical 2, and then divide by this coefficient 2. So we have sine of x equals negative radical 2 over 2. The fact that we recognize that value is a good sign, right? Connor, give me one place where the sign is negative radical 2 over 2.
That'd be 7 pi over 4.
Okay. And another place, Will. Five pi over 4. Okay, so we have two places, 5 pi over 4 and 7 pi over 4, where the sign is negative radical 2 over 2. And then we will add plus the period times n to those solutions to describe that this is going to happen every period of that function. And we have two answers. When you have a ratio that is not a ratio on a quadrantal angle, you'll more than likely have two places that it'll occur. All right? If you have a ratio that's coming from a quadrantal angle, sometimes there's only one of those, okay? Like the sign is only -1 at one place, okay? But most of the time you're gonna see 2 answers for each, okay? All right, we will step it up a notch. Actually, kind of a big notch. Okay, 2 sine squared x plus 3 cosine x equals 0. Is this linear? No. So we need to think about maybe, is there something that we can factor? We don't even have the same kind of function, do we? Okay, and that's a problem, all right? It would be really cool if there was a way to write one of these in terms of the other, so that we had all sines or all cosines. Jackson, do you have an idea?
Could you, like, instead of writing it as sine squared, could you do 1 minus cosine squared?
Could we do that? Sine squared is the equivalent of 1 minus cosine squared. So yes, we can replace sine squared with that using the Pythagorean identity. And now we have an equation where every trig function is a cosine. Okay? So let's go ahead and distribute this. We have 2 minus 2 cosine squared x plus 3 cosine x equals 0. Now I know it's not in order yet, but what are we working with right now? We are working with a quadratic. And how many terms are there? 3. We have a trinomial. Okay? And when we have a quadratic that has 3 terms, what do we typically have to do with that? Factor. Okay. Now, I'm going to reorganize this. Do we like to have a negative leading coefficient when we factor? No. So I'm going to do 2 things at once here. Okay, I'm going to reorganize this so it's cosine squared, then cosine, then the constant. But I'm also going to move everything to the other side of the equal sign so that we have a positive leading coefficient. So I'm going to add everything over there. So we have positive 2 cosine squared x minus 3 cosine of x minus 2. You want positive leading coefficients to factor, otherwise it's going to give you a headache. Okay? I mean, you can do it, but this definitely makes it easier. Okay? So this is why we practiced factoring last week. Okay? Well, we know we need a cosine of x times a 2 cosine of x. Well, and the only place for 2 to go is here, because we can't have 2 terms with a GCF when we factor. Which one needs to be negative, the 2 or the 1? The 2. So this will make a negative 4 cosine x, and this will make a positive 1 cosine x. Remember, if it helps you, go off to the margin of your paper and write 2c squared minus 3c minus 2, and factor it in terms of c's, and then come back and factor your cosine equation. Okay? I'm probably not going to do that anymore up here, but you know that you can go off to the side of your paper and do that, and that's not a problem. Okay? So, now, we have 2 factors that equal 0. Just like back in the old days, we're going to take these 2 factors and do what with them? Okay? We're going to set them equal to 0. Okay? So now we have 2 mini equations we need to solve. Would you like to start on the left or the right? I'll let you guide me. Left? On the left side, we have cosine of x equals 2. Okay, when is a cosine equal to 2?
Another unit circle to the right.
Another unit circle to the left. But you don't know that value?
I wasn't made it, which was
Okay. Can someone help Gabe out? Where's the cosine equal to 2? Is the cosine ever equal to 2? Why not, Kelsey? Because it's not. Yes, good. Yes, the range for sine and cosine is -1 to +1. 2 is outside of that range. We don't get a solution there. Algebraically, we get that the cosine of x equals to 2, but trigonometrically, that doesn't make sense. Okay? So, hey, that's nice, right? That's like less work we have to do. Okay? So now we need where the cosine of x is equal to -1/2, which happens at 2 pi over 3 and 4 pi over 3. And then we add in the period times n. Okay? All right. It is lunchtime, so as soon as you get those answers written down, you can go, and we will pick up where we left off when you get back. All right. We kind of abruptly finished this problem. Were there any questions on those answers? Okay. If you get a situation like here where the range, it doesn't fit the range, make sure you show me that you thought about it and like cross it out so I can still see that you thought about it, but that you realize that there's nothing that will make that work. Okay. All right, next example. Okay, so here we have something on both sides of the equal sign. What do you think we should do? You think we should divide by cotangent x? Who else thinks that we should do that? Is actually not allowed. Let's think about why. Is it possible for cotangent of x to be 0? Yes, yes it is. Are we allowed to divide by 0? We are not. So even if there is a chance that that could be 0, we are not allowed to divide by it. Okay? Do not ever divide by a trig function. Instead, we can subtract it to the other side, and then what can we do with those two terms? We can factor out the cotangent. So never, ever, ever divide by a function. Subtract it over, and then you would be able to factor it out. Okay. All right, so we have two factors now that equal 0. So we can take each of them. Cotangent of x equals 0. And cosine squared x minus 2 equals 0. Okay. All right, we'll start on the left side. The cotangent is equal to 0. Where? Caroline? Pi over 2? Is there another place? Okay. And what is the period of tangent and cotangent? Pi. Okay. Now, these are both of the answers. Now, let me ask you this. How far apart are pi over 2 and 3 pi over 2? They're pi apart. So, by saying pi over 2 plus pi n, that includes 3 pi over 2. So technically, we would only have to write one of these, and then the other one is covered. Okay? That's going to happen every time when you are answering cotangent and tangent problems. Okay? However, if you put both answers, I am never going to be upset about that. Okay? It's just being redundant. All right. How about over here? We have cosine squared of x equals 2. Remember that when you square root both sides, you have to account for plus or minus that radical value. That will pop up a couple times in your homework. All right, where does cosine equal radical 2? Radical 2. What do you say, Amanda? It doesn't. Okay, if this was radical 2 over 2, we would be in business. Okay? But it's radical 2. And radical 2 is approximately 1 point something, which means it's not going to give us a solution. Algebraically it works, but trigonometrically we don't have any values that can make that happen, so there's no solution from that factor. All right. Okay, we have 2 more examples. Okay, ideas. Okay. And why do you think we should do that? Okay, so the fact that there's secant squared and tangent is kind of awkward. So Gabe suggested to change secant squared to its Pythagorean identity, which is what? Tangent squared plus 1. Okay, now, if we want to factor anything, we have to set it equal to 0. So when we subtract that 1 over to the left side, what happens? They cancel out. So we're left with a really nice equation. Tangent squared x minus tangent x equals 0. Hey. All right, Jen, what can we do? Okay, so we have 2 terms, both have a tangent. So we can factor out the tangent, and then we are left with tangent x plus 1. Remember, we have to set equal to 0 in order to be able to factor. Now that we've factored, we can look at each factor equaling 0. Yeah. It should be minus 1. Thank you. That will make a difference in their answer, won't it? All right, Amarissa, where is the tangent equal to 0?
0 or
Mhm. Or where? Uh-huh. So 0 or pi. And so there are our two answers. Will? No, that would have to be tangent squared minus 1 to be a difference of squares. That's what you're visualizing. Okay. But if that were the case, yes. Okay. And then we add plus our period times n. Now, remember this is going to happen every time with tangent, where your two solutions are going to be pi apart, which is your period. So you can condense these to just write as one. You could write, is this what you're going to ask, just pi n? Yeah, you can condense those down to pi n. Now, if you write both of those, you're not going to be upset, not going to count it wrong. Okay? How about over here? Tangent of x equals 1. Molly, where does the tangent equal 1?
Pi over 4.
Anywhere else? Mm-hmm. Okay, and then we add period times n. And since it's tangent, our solutions are pi apart, which is the same as that period. So you could just write one of them and it includes both of them. Okay? So you could write 4 answers here. I wouldn't be upset, but you could only write pi over 4 plus pi n and 0 plus pi n. Those are the answers that the back of the book will have. Okay? All right. Last example. Okay? One curveball that I'm going to throw at you. It's not really a curveball, it's just something different. Why is this one different? They all have variables. It has a coefficient with that variable. That's what you're, okay, it's okay. It's a Friday, you're a 5-day week. Okay, so our angle isn't just the variable, it's a number times that variable. Okay, so how is that going to affect our answer? Now, we are still going to solve for cosine. So we have 2 cosine of 3t equals 1. And the cosine of 3t equals 1/2. That 3 is stuck inside. You cannot, I repeat, you cannot divide by that 3. That's not how you get it out. You can only divide by numbers that are being multiplied to the function, and that is not the case. Instead, okay, when we were over here, we said, okay, sine of x equals this, and so then we named the angles that x can be. We're going to do that same thing over here. All right? What are the 2 places that cosine is 1/2? Pi over 3 and 5 pi over 3. And then we add in plus the period times n. Okay, those are the 2 angles that satisfy cosine as 1/2. However, our angle is 3t. So then, to actually write our solutions, we have to divide by 3. So here, t equals pi over 3 divided by 3 plus 2 pi n divided by 3. And here, t equals 5 pi over 3 divided by 3 plus 2 pi n divided by 3. And those are your solutions. Okay, so you first have to name which angles satisfy, and then if that angle has a coefficient, that's when you divide it, after you've had those solutions. Okay. Questions about that example? Okay, this is what I'm going to do. I am going to, whoops, that's not what I want yet. I'm going to give each pod a problem. Each pod will have a different problem, and I want you to work together to solve the problem. Once you have an answer that you all agree on, I will come and check it, and then you can reference your gold sheet to begin your homework. Okay?